You're listening to DTF-HN for July 21st, 2026. I'm your thermodynamically irreversible host, Jack Haxman. We are your daily tech feed for Hacker News, a website where mass complaints about text editors coexist with genuine brilliance. Today, the commons are winning and the gatekeepers are sweating. Strap in. Alibaba's QN team just dropped QN Image 3.0, their latest image generation model. The headline capabilities are genuinely impressive. Complex layout generation from long prompt, newspaper pages, storyboards, exam papers, all from up to 4,500 tokens of input. That's a real technical achievement. Generating coherent complex documents with mixed text and imagery is one of the hardest problems in image synthesis, because you're fighting the tension between global composition and local detail fidelity. The fact that they're solving this at the layout level, not just the single object level, matters. But there's a problem, and the Hacker News comments cut straight to it. Not a single word about releasing the weight. Let's be precise about why this matters. Quinn has built enormous goodwill in the open-source AI community, other language models. Quinn dieuwen iver land coding variants, the Vaden language models have been some of the most important open-weight releases of the past 2 years. They've been genuine contributors to the commons. Engineers around the world have built on Qwen models, fine-tuned them, deployed them in products that would never exist if the weights lived behind an API wall. So when Qwen announces a new model with zero mention of weight release, the silence is loud, and the community noticed immediately. The technical question here is straightforward. Image generation models are expensive to train. The datasets are enormous. The compute bills are real. But that's been true of every Qwen model they've open-sourced. The constraint hasn't changed. So what changed in the calculus? One possibility is that this is just timing. Weights come later, after an API-exclusive window. Alibaba Cloud sells inference, and a head start on hosting matters commercially. If that's the case, fine. Understandable. Ship the API. Release the weights in a few weeks. Everyone wins. The other possibility is that image generation is where the open weight strategy ends. That this is the capability where the business case for openness breaks down, where the revenue from API access outweighs the ecosystem value of open weights. If it's the second case, that's a genuine loss, because someone asking whether they can run this locally on a 16-gigabyte GPU, that person is exactly who open weights serve. The researcher in a country without cloud credits. The indie developer who can't afford per-image API pricing. The tinkerer who wants to fine-tune on their own aesthetic. The capability is real. The architecture is impressive. But capability behind a wall is a product. Capability in the open is infrastructure. Qwen has been infrastructure before. The question is whether they still want to be. Infrastructure comes in many forms. Sometimes it's a model. Sometimes it's a library that makes your computations dramatically smarter. In 16 Yibs Koan, Dan Bricklin watched his professor at Harvard Business School erase and recalculate an entire financial model on a blackboard. Because one input changed. Every cell, every dependency, every downstream result recomputed by hand. That frustration became VisiCalc. The first spreadsheet, and the core insight was simple. When one value changes, only recalculate what depends on it. Don't redo the whole board. 47 years later, Jane Street's incremental library is that same insight, formalized with mathematical rigor and implemented in OCaml. It's a framework for self-adjusting computation. You define a directed graph of values and their dependencies, and when an input changes, the system propagates exactly the minimum set of recomputations needed. Nothing more. The engineering here deserves real admiration. This isn't a hack or an optimization pass bolted onto existing code. It's a computational model rooted in Umut Akar's academic work on self-adjusting computations, brought into production at one of the most demanding trading firms on the planet. Jane Street processes enormous volumes of market data in real time, and every microsecond of wasted recomputation is money. Incremental is how they make that tractable. Run this forward. Imagine every application that currently rebuilds its entire state on every tick. Every dashboard that requeries everything, every UI that re-renders its full tree, every pipeline that reprocesses complete datasets because one record changed. Now imagine each of those systems knowing precisely which outputs are stale and touching only those. That's not a marginal improvement. That's a category shift in how we think about reactive systems. The comments surface something fascinating. This pattern is everywhere under different names. JavaScript developers know it as signals. Clojure had Javelin. Goldman Sachs apparently built something similar for instrument pricing 30 years ago, complete with internal jargon about node purpling. The same idea keeps getting independently discovered because it solves a fundamental problem in computing, the gap between what changed and what you recompute. And here's what mattered. Jane Street open-sourced this. A firm legendary for its competitive secrecy looked at a core piece of their infrastructure and put it where anyone can reach it. The entire library, the documentation, the dependency tracking algorithms refined under real production load. Available on GitHub. MIT licensed. The tools exist. The theory is proven. The implementation is battle-tested. Someone at Jane Street decided the world should have this, and that decision is how open source wins. Not through ideology, but through engineers recognizing that shared infrastructure lifts everything. Now, shared infrastructure lifting everything. Pause. That principle doesn't stop at company walls or national borders, which brings us to story 3. $3 per million input tokens. That's what Kimi K3 charges. Write that number down, because it tells you everything about where this industry actually is versus where people think it is. There's a debate raging right now about Chinese AI models, and it's almost entirely the wrong debate. The question everyone's asking is whether Kimi K3 matches the frontier. The question they should be asking is why free and open weights still cost $3 per million tokens to run. Let's break this down to first principles. Software had zero marginal costs. That was the whole game for 20 years. You build it once, you ship it to 1 billion people, and unit number 1 billion costs the same as unit number 1, which is nothing. That's what made aggregation theory work. That's what made Google and Facebook possible. The economics of AI are fundamentally different, and most of the discourse hasn't caught up. When someone releases an open weights model, they're giving you the R&D for free. The research, the training runs, the months of compute. That's generous, and it matters. But R&D is a fixed cost. It's already spent. What they can't give you for free is inference. Because every time someone asks a question, silicon has to think. Electrons have to move. And someone's power bill goes up. The marginal cost is real. It's not zero. It's not close to zero. And it scales linearly with usage. This is actually the interesting part that the hand-wringing about China misses entirely. The frontier labs want you focused on who built the model and what flag flies over the data center. Meanwhile, the economic reality is simpler and more consequential. Inference costs money. Every model. Everywhere. From every country. The question isn't which nation's model you're afraid of. The question is, who controls the infrastructure that runs it? An open weights model you can audit. fine-tune, and run on your own hardware is categorically different from a closed model behind an API, regardless of what country either one comes from. One of them you can verify. The other you take on faith. The commenters grasped this instinctively. As one put it, the bigger distinction is open versus closed, not made in America versus made in China. The real fear shouldn't be Chinese models. It should be any model you can't inspect, can't modify, and can't run yourself. Let the frontier labs compete on capability. Let them win by being better. But the moment safety becomes the argument for pulling up the ladder, for locking down weights, for making sure only the right companies get to play. That's not security. That's protectionism with a halo. The weights are out. The costs are real. The only question left is, who gets to run them? Moving on. What happens when the most famous name in open hardware starts competing with the ecosystem its community already built? Arduino just launched a line of plug-and-play sensor modules designed for long-range projects. Think LoRa connectivity, snap-together hardware, no soldering required, and the immediate reaction from the builder community is basically, we already have this. SparkFun's ThriQuick system, Adafruit's Stemma QT. These modular, connector-based sensor ecosystems have existed for years, built by companies that grew up inside the Arduino community itself. Now, let me play devil's advocate for a second. You could argue Arduino is late, that they're just slapping their logo on a solved problem. But run this forward. Arduino isn't a parts vendor. Arduino is the reason most people touched a microcontroller in the first place. When Arduino blesses a form factor, it becomes the default in every classroom, every workshop, every YouTube tutorial aimed at beginners. SparkFun and Adafruit built brilliant ecosystems. But they built them for people who already know what I2C means. Arduino builds for the person who doesn't know that yet. The more interesting tension is in the comments. Someone points out that the old Arduino, it's a Mega 32AP on a breadboard that you could move to a custom PCB with minimal fuss. That simplicity was the whole point. And they're right. There's a version of Arduino's evolution where plug-and-play convenience becomes a wall between the user and understanding, where the module is a black box instead of a learning tool. But here's the unintended comedy of hardware ecosystems. Every generation of too easy tools produces a generation of builders who outgrow them. The kid who starts with plug-and-play LoRa modules today is designing custom PCBs in 3 years. The abstraction isn't the ceiling, it's the on-ramp. One commenter asks whether Arduino's flirtation with closed source a few years back should still count against them. Fair question, but the answer is in the architecture. Their hardware designs are open, their software is open, and the community fork that happened during that drama proved the whole point. You can't close what was born open. The community won't let you. The real story isn't whether Arduino invented modular sensors. They didn't. The real story is that open hardware has gotten so mature that the argument is about which open ecosystem to use. That's the kind of problem you want to have. Open ecosystems maturing is a theme today, and nothing proves that like the Linux kernel picking up a trick straight from user. One commenter on this thread writes, quote, Nix has caused so much busy work to be created through the entire Linux ecosystem. Rather than fixing their own project, they force work upon so many others. That's the comment I want to start with. Because what actually happened here is the exact opposite of what that commenter describes. Fareed Zakaria wanted relocatable binaries in Nix. The problem is real and specific. ELF binaries on Linux have a field called PT interp that points to the dynamic linker, and that path is hard code at build time. Absolute paths. Baked in. If you move the binary, the interpreter path breaks NICs, which stores everything in content-addressed paths under /nide/store, has been working around this limitation for years with wrapper scripts and patch health hacks. The variable $origin, which the dynamic linker already understands for shared library resolution, could solve this if the kernel honored it when selecting an interpreter. Zakaria sent a patch to the Linux kernel mailing list proposing exactly that. Direct $origin support in the VFS layer. And here is where the story gets genuinely interesting. Christian Bronner, the VFS maintainer, didn't just accept or reject the patch. He proposed something far more general. Use eBPF through binfmt to make interpreter selection programmable. The technical result is elegant. A small eBPF program registers with binfmt pattern matches on LELF magic bytes, and dynamically computes the interpreter path relative to the binary's location. The kernel jits this to native code. The verifier guarantees safety. The whole mechanism is about 30 lines of C, and it doesn't just solve $origin. It makes interpreter selection a programmable surface. You could replace QEUO's binfmt registration scripts. You could invent new LF segment types and handle them without further kernel patch. This is a case study in how open development is supposed to work at the infrastructure level. An outsider brought a real problem to a kernel subsystem maintainer. The maintainer, engaging in good faith, recognized a more general solution hiding inside the specific request and prototyped it on his own vacation because the problem was genuinely interesting. The patch series is heading into -next. The commenter who called this busy work forced on others missed what happened entirely. Nobody was forced to do anything. An engineer saw an interesting problem, found a general solution, and wrote the code. The kernel gained a new capability that benefits far more than commentary. That's not a burden. That's how infrastructure evolves. Someone scratches an itch, and the fix turns out to be load-bearing for use cases nobody anticipated yet. 30 lines of eBPF. Programmable interpreter selection. Merged because it was a good idea. Full stop. We talked earlier about AI agents doing real work. Pause. Kimi Work is pushing that idea further than most. Copying is how knowledge compounds. Let's get that out of the way first, because the loudest reaction to Kimi Work, Moonshot A's new local agent, is that it looks like Codex, the UI, the task runner, the agentic loop, and the critics aren't wrong. It does look like Codex. The question nobody in that comment thread is asking is, why should that bother anyone? Here's what Kimi Work actually does. It mounts your local file system. It browses the web autonomously through something called WebBridge. It runs Python in the background. It schedules tasks. You point it at a folder full of PDFs. Tell it to find your quarterly reports and summarize them. And it does. Without uploading your files to someone else's server, the agent runs locally. Your data stays where it is. Now, the engineering here deserves real attention. Building a local agent that can coordinate file system access, web retrieval, code execution, and scheduled automation in a single loop is genuinely difficult. The orchestration layer has to manage tool selection, error recovery, context windows, and state persistence across session. All while running on consumer hardware. That's a non-trivial systems problem. Anyone dismissing this as a weekend clone hasn't built one. But here's the question that keeps nagging. If it's this easy to replicate the interface patterns that OpenAI and Anthropic pioneered, and multiple commenters note exactly this, then what was the moat? First mover advantage evaporates the moment someone ships the same capability at a fifth of the price. $3 per million input tokens on Kimi K3. The architecture of these agentic systems was never the secret sauce. The secret sauce was supposed to be the model. And if Moonshot's models are good enough to power a competitive local agent, then the competitive landscape just flattened considerably. One commenter captured it perfectly. People saying copy aren't wrong, but if the copy runs at a fifth of the price, you don't have a knockoff. You have price discovery. This is what open competition looks like when the building blocks are accessible. The tools exist. The patterns are documented. Someone in Beijing looked at the state of the art, rebuilt it, undercut it, and shipped. The correct response isn't outrage. It's recognition that the game just changed. And the builders who treat agentic interfaces as a commodity rather than a moat are the ones who'll still be standing when the dust settles. Sometimes open source just makes you smile. This one turns every HTML button and slider into a wobbly, squishy, delightful physics simulation. Every single component on the page runs its own animation loop at 8 milliseconds. Every button, every toggle, every slider. Each one independently requesting animation frames, redrawing, recalculating physics. A commenter dug into the source and found the entire document repainting constantly just to make buttons wobble. And this is exactly the kind of project that matters. In 1984, Bill Atkinson built MacPaint with a constraint that would horrify modern developers. 64 kilobytes of heap memory on a machine running at 8 megahertz. Every pixel operation was hand-tuned. The result wasn't just functional, it was joyful. People who'd never touched a computer suddenly wanted to draw. The interface invited play, and play invited mastery. Jelly UI is chasing that same instinct. One developer building under the name Bempson ships an entire web components library with 0 dependencies. Real form controls, checkboxes, radio buttons, sliders, toggles, wrapped in soft body physics that respond to touch like physical objects. Dark mode, right to left support, Gaga color tokens baked in from the start, MIT licensed, built in the open, free to use. The performance criticism is valid and worth taking seriously. A physics simulation running continuously across dozens of elements will punish low-powered devices. The click behavior breaks platform conventions. Holding and dragging away should cancel the action, and right now it doesn't. These are real problems that real users will hit. But here is what deserves a straight take. The web has spent 15 years optimizing for conversion funnels and engagement metrics. Interfaces got flatter, more utilitarian, more hostile. The humanity drained out of the medium. Someone looked at that trajectory and decided to make buttons that feel like gummy bears, and then gave the code away. The accessibility work tells you this isn't a toy. Reduced motion media queries are respected. Color contrast meets standards. This is someone who cares about craft building something generous and putting it where anyone can reach it. The physics loop needs optimization. The click handling needs fixing. These are engineering problems with engineering solutions. The impulse behind the project. That software should feel alive, that interfaces deserve texture, that one person can ship something delightful and hand it to the world. That impulse is sound. The code is open. Anyone can make it better. Now for something completely different. You know a CPU design has arrived when someone gets Doom running on it. I once spent 3 weeks debugging a memory controller that worked perfectly in simulation and failed catastrophically on real hardware. The timing margins were off by nanoseconds. Nanoseconds. And that experience is exactly why this project from Armand Gomes and Liam makes me want to stand up and applaud. Building a CPU from logic gates is like building a violin from raw wood. You can understand every principle, read every book, study every schematic. And the thing still won't sing until your hands learn what the theory can't teach. These two built a pipelined RISC-V processor in Chisel, a hardware description language, deployed it onto an FPGA, and then had the audacity to ask, can it run Doom? The answer required solving two problems that sound simple and absolutely are not. First, memory. Their FPGA's block RAM holds less than a megabyte. The Doom shareware WAD alone is 14 megabytes. They needed DDR3 integration, which means dealing with variable latency, wide bus widths, and timing that laughs at your neat pipeline stages. In their original design, every memory access took exactly one clock cycle. Beautiful, predictable pipeline. DDR3 memory is none of those things. Their solution was cache, and not textbook cache. Cache that had to handle the ugly reality of in-flight memory, requests getting invalidated by pipeline redirections. When a branch prediction fails, and the fetch stage needs a different instruction, but DDR3 already has a request in progress, you need to track that the next response is garbage, and throw it away gracefully. That kind of detail separates people who understand architecture from people who've built architecture. The second problem was speed. Liam is working on out-of-order execution. The same technique that makes modern processors fast, implemented from scratch on an educational project. They also added the XEMMOL extension for hardware multiplication, which Doom's rendering engine absolutely demands. The whole thing is open. The chisel source, the design decisions, the war stories about what broke. This is how knowledge compounds. Two engineers build something real, document the pain, and leave the door open for the next person to walk through. The video got millions of views, not because running Doom is novel, but because building the machine that runs it is genuine craft. Every gate placed with intention. Every pipeline stage earned. The tools exist. The FPGAs are affordable. The ISA specification is open. What these two built in their own time, major companies once needed entire teams to accomplish. That gap is closing, and it's closing because open hardware and open knowledge let builders stand on each other's shoulders instead of waiting for permission. We talked earlier about machines surprising their creators. Well, mathematicians are getting outcounterexampled by AI. Mathematicians have spent decades trying to prove Erge's unit distance conjecture. In May, ChatGPT disproved it. Found a counterexample. Used a deep theorem from 1860s number theory. As a wrecking ball, nobody thought to swing at this particular wall. That alone would be worth talking about. But what happened next is the part that reshapes the landscape. Within a week, logical intelligence auto-formalized the proof in Lean. The interactive theorem purveyor that lets you verify mathematics against the actual axioms. No trust required. Then, Boris Alexeyev at OpenAI pointed their soul model at the full problem and told it to formalize everything, all the way down. 3 weeks later, 1.2 million lines of Lean code. A complete formal proof from axioms. For context, Lean's entire community-built math library, 9 years of human effort, is 2.3 million lines. Let's pull this thread. The formalization includes hard theorems in global class field theory. This is graduate-level number theory that takes humans years to internalize, let alone encode in machine-checkable logic. A year ago, Formalizing it seemed like fantasy. Now it exists as verified code anyone can read and run. And that word, anyone, is where this gets interesting from a bootstrapism perspective. Kevin Buzzard, the mathematician writing about this, ran the AI-generated code in a sandbox because Lean can execute arbitrary commands. Smart, but he also made a crucial observation. Large AI-generated developments of mathematics are now inevitable. The question isn't whether machines will produce novel mathematical knowledge. It's whether that knowledge stays open. The code is public. The proofs are beta-boy-able. The counterexamples are real. This is what acceleration looks like when the artifacts are transparent. Not a black box claiming results, but a formal proof chain anyone with a laptop can check. Mathematics has always been humanity's most democratic discipline. You don't need a lab or a license. You need logic. Now the machines are doing logic too, and the verification is open. The tools compound. The knowledge compounds. The counterexamples just got faster. So what happens when you apply that same rigorous mathematical thinking to something as fundamental as how we store numbers? In 1965, IBM engineers faced a problem with the system 360. They needed to pack decimal digits into binary memory. Each decimal digit needs about 3.32 bits. But you can't use a third of a bit. They settled on 4 bits per digit. Binary-coded decimal, wasteful, inelegant, but fast to unpack on the hardware they had. That trade-off, density versus decode speed, hasn't gone away. It's just gotten weirder. Compiled needed to pack ternary weights for bitnet B1.58. Each weight is -1, 0, or 1. 3 possible values. Information theory says you need log base 2 of 3 bits per value. About 1,585 bits. You can't use 1.585 bits. You need a whole number of bits for a whole number of tricks. Here's where the numerology gets beautiful. 3 to the 5th power is 243. 2 to the 8th power is 256. 5 ternary digits fit into 8 binary bits with 13 values to spare. That's 1.6 bits per trick. 99% of theoretical perfection. The IBM engineers would have wept. But packing is the easy part. The trick is unpacking without division. SIMD hardware, the parallel pipelines that make modern inference fast. Generally can't do integer modulo. Compilate solution is to store the byte as a fixed point fraction. Multiplied by 3, the top bits give you the next digit. The bottom bits give you the remainder. Repeat 5 times. Pure multiplication and bit shifts. The kind of thing GPUs eat for breakfast. The entire scheme is 11 lines of Python to pack. 8 to unpack. The C verification program confirms it's lossless for all 243 possible values exhaustively. No edge cases, no approximations. This is what bit-level engineering looks like when the code is public and the math is real. A packing scheme anyone can read, verify, and ship. This has been your daily tech feed for Hacker News for July 21st, 2026. This podcast is entirely AI-generated. Scripts by Claude Sonnet 4.7. Voice by Quen 3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something and leave the door open behind you. We'll see you back here tomorrow.